In the last module, we saw how to price caplets and floorlets. Well, there are other liquidly traded fixed income derivative securities in the marketplace, and they are swaps and swaptions. So in this module, we're going to see how to price swaps and then how to price options on swaps, which are called swaptions. Again, we'll be focusing on the binomial lattice model, and by pricing them in this model, we will also understand and reinforce our learning behind the mechanics of these securities. So here again is our familiar short rate lattice. We've seen it now many times, beginning at R equal to 6%, rising by a factor of U equals 1.25, or falling by a factor of D equals 0.9. What we want to do initially in this module is to price an interest rate swap with a fixed rate of 5% that expires at T equals to 6. The first payment will occur at T equal to 1, and the final payment will occur at T equal to 6. Now, the payment at each node will be the following. It will be plus or minus, depending on whether you're long or short the swap, of the short rate that prevails at that node minus K. But that payment is made in arrears at time T equals I plus 1. So again, like the caplet we saw in the last module, we're going to assume that the cash flows in our swap are paid in arrears, which is a typical situation that occurs in practice. And so just to give you an idea, so for example, up at this node here, 18.31%, well, the cash flow at this node will actually be 18.31% minus 5%. But actually, I should say that this is the cash flow that is determined at this node. The cash flow itself will not take place until one period later at time T equal to 6. Similarly, the cash flow at this node will be 11.72% minus 5%. That is the cash flow determined at that node. It will be paid at time T equal to 4. And so all of the nodes here will have cash flows equal to these values minus 5% to be paid one period ahead. How do we price the swap? Well, let's go to that. So what we're going to do is to figure out again how much the swap is worth at the final node. Now the final node again is T equal to 6, but we don't want to record the final values at T equal to 6 because, for example, if we find ourselves at this node here, well, it won't be clear how we got here. Is the payoff at this node because we were at this prior node or we were at this prior node? And depending on which node we were at in the previous period, we'll get a different cash flow up here. So this is the exact same situation as we saw with the caplet in the previous module. It's actually much easier to record the cash flows at the nodes at which they occur, but discount them suitably to reflect the fact that they are paid in arrears or one period later. And that's what we're going to do here. So for example, this 0.0723 that we have highlighted up here, well, that is equal to the cash flow, or 55 minus K, divided by 1 plus, or 55. So or 55 minus K is the payoff of the swap, but this swap takes place at time 6, so we have to discount it by the short rate that prevails at this node. And so we get this value, which is 0.0723 at time T equals 5 and state 4. Here's another sample calculation, 0.1686. So where do we get this from? Well, we're going to get that from our standard risk-neutral pricing. Maybe we should write out our risk-neutral pricing again here. So in this case, risk-neutral pricing takes the following form. Let ST be the generic value of some security that we want to price. Then we know that ST is equal to the expected value, conditional on time T information, under the risk-neutral probabilities of the payoff or the value of the security one period ahead, ST plus 1, but also the swap actually has intermediate cash flows, or coupons if you like. So we must also include these cash flows, CT plus 1, discounted by 1 plus or T. So this is our risk-neutral pricing, or familiar risk-neutral pricing for security that has intermediate cash flows. So this 1.686, for example, how is that calculated? Well, it is as follows. It is 1 over the short rate that prevails at that node. So that short rate is 9.38%, and we can check that by going backwards. Here it is, 9.38%. And we have the cash flow. So this is our CT plus 1. This is the payment that takes place one period ahead. It is the cash flow determined at this node, but it is paid one period ahead. And these terms here give us the possible values of ST plus 1. So either 0.1793 if we go up, or 0.1021 if we go down. So this is just risk neutral pricing. We work backwards in the lattice until we get to time t equals 0. That gives us the initial arbitrage-free value of the swap, and we find it's 0.0990. And again, to keep in mind here, this is the fair value of the swap for a notional of $1. Right? We're multiplying each of these payoffs, these cash flows, by $1. In practice, maybe you'd have $100,000 or $1 million, and so you should be multiplying this value then by that notional of $1 million or $100,000. Now let's consider how to price swaptions. Swaptions, like swaps, are very liquid securities. They're traded all the time, used by many market participants to both hedge interest rate risk as well as speculate on interest rate risk. A swaption is an option on a swap. So what we're going to do is we're going to consider a swaption on the swap of the previous slide. We're going to assume that the option strike is 0%. This should not be confused with the fixed rate of the underlying swap. Remember, the fixed rate of the underlying swap was 5%. So we're going to assume that the option strike is 0% and that the swaption expiration is at t equals 3. In other words, the option on the swap expires at t equals to 3. Therefore, at time t equals to 3, if you own the swaption, you have the right to exercise or enter into this swap for a value or a strike value of 0. So the payoff at time t equals to 3 is going to be the maximum of 0 and S3. You will only exercise the swaption at t equals to 3 if S3 is positive. If S3 is negative, then you won't exercise, the maximum will be 0 and you'll do nothing. So how are we going to price this swaption? Well, actually it's going to be very simple. We're going to use our calculations from the previous slide, which we see here, to get the value of the swaption, or rather to get the value of the swap at t equals to 3. We're going to replace this column of prices with the maximum of 0 and this column. That will give us the payoff of the swaption at maturity, t equals to 3, and then we will just calculate the fair value of this payoff by working backwards in the lattice using risk-neutral pricing. One thing to keep in mind though, however, is that when we're working back from t equals 3 back to 0, we no longer include the underlying cash flows of the swap. And that's because the holder of the swaption does not get those underlying swap cash flows. The holder of the swaption will only get the cash flows associated with the swap if they exercise at t equals 3. And then they will get the swap cash flows for all time periods greater than t equals 3. They will not get them for the periods before t equals 3. So here are some sample calculations again. For example, so if you look at t equals to 3, this is the payoff of the swaption. So in fact, all of these values here from t equals 4 and 5 are simply the values that we see that we calculated earlier for the underlying swap. So we see 0.0512 here. Well, that's the same 0.0512 here. Down here, however, is the value of the swaption at maturity. And now this is equal to the maximum of 0 and S3. So if you recall, the only change is actually down here, because in the underlying swap value we had a negative value, minus 0.0085 at this node, but now the holder of the swaption would not choose to exercise at this node. Why would they buy something for 0 when it has a negative value? They won't do that. So they will exercise, however, at all of these 3 nodes, because at these 3 nodes the swap has a positive value. So certainly the holder of the swaption will exercise at these 3 nodes and receive these 3 payoffs. So what we have is, here are the values, the payoff values of the swaption at maturity at t equals to 3. It's equal to the maximum of 0 and S3. And now we actually just compute the fair value of the swaption by computing the value of this payoff backwards in the lattice. So here, what we're using in our risk-neutral pricing again, if you like, I won't use S here, I'll say Z. So ZT is equal to the expected value of Z t plus 1 divided by 1 plus RT. This is our risk-neutral pricing for the swaption. Note I don't have any intermediate coupon or cash flow in here, and that's because the swaption doesn't pay any intermediate coupons or cash flows between t equals 0 and t equals 3. So I just iterate this backwards to get the value of 0.0620 as being the value of the swaption at t equals 0. So here's a sample calculation. 0.0908. Well, 0.0908 is just 1 over 1 plus R1. R1 is going to be 7.5% of this node times the expected value of the swaption 1 period ahead. Well, the risk neutral probabilities are a half and a half. These are the values of the swaption 1 period ahead, 0.1286 and 0.0665, and so that's how I get 0.0908. You can see all of these calculations performed in the spreadsheet. They're very easy to do. We see again here that we have our usual short rate lattice that we're using throughout. So these are the details here. I won't go through them again. Down here we calculate the value of the swap, the underlying swap. So it has a fixed rate of 5%. Here we see the payoffs of the swap at time t equals to 5. In fact, these are the values of the swap, because remember the payoffs occur at time t equals to 6, but we discount them back 1 period to reflect that the swap cash flows occur in arrears. So we do that at time t equals 5. We now work backwards in the lattice using risk neutral pricing. So for example, down here we see that the value of the swap at this node is the payoff that's determined at that point. So that's the cash flow identified up here, plus the expected value of the swap 1 period ahead, and that's given to us by these terms here. And of course I have to discount both of these quantities, the cash flow because it's in arrears and the value of the swap 1 period ahead, by 1 plus the short rate at that node. And that's how I get this expression here. It's in bold again because you can actually just enter the formula into this cell and then drag this formula throughout the rest of the lattice to compute the prices of the swap at every node. We find an initial swap value of 0.0990. To compute the fair value of the swaption, well, all we do is we just repeat really what we did for the swap. We just calculate the value of the swaption at maturity. So we see it down here. In this case, it's the maximum of the swap value, which is given to us here, and 0. So that's how we get these values down here. And now we just use risk neutral pricing to work backwards in the lattice. Note that at any cell in this lattice, we don't have any intermediate cash flow, or we don't have the cash flow associated with the swap at that time. And that's because the holder of the swaption does not get any of those cash flows or pay any of those cash flows until such time as they exercise the swaption. So we just work backwards and find an initial value of 0.0620.